Welcome to Review, Unit 3. In Section 1, we covered a bunch of definitions. So just to remind you that you're mixing two things together. Usually when you're talking about a solute and a solvent, you're talking about something that the solute is usually the solid and the solvent is the liquid. And liquid's usually water. So the solute is being dissolved and the solvent is doing the dissolving, and you put those two things together, you get your solution. The next set of definitions all sort of go together, all different types of solutions. So we have our saturated solution, which is the perfect amount of solute and solvent. To me, it's kind of theoretically impossible. It's like you probably got either a little too much solute or not enough. But anyway, we'll consider that to be the saturated solution. Supersaturated is too much solute. You make that Kool-Aid, you put too much sugar in, you got a bunch of sugar at the bottom that won't dissolve. And the other one is the unsaturated solution, and it can dissolve more solute. So again, you make that Kool-Aid, you put the sugar in, but you didn't put enough sugar in, and now it tastes really bad. So that would be an unsaturated solution. Soluble, insoluble, and solubility. So earlier in Unit 1, we covered soluble and insoluble. So something that's soluble, that's going to readily dissolve in water, that's in the aqueous state, and something that is insoluble will be a solid. So refer to your solubility rules for those two. And then solubility is just sort of describing how soluble or insoluble everything is. And we've sort of taken a hard line on this, saying, it is soluble, it isn't soluble. But fact is that, even things are more, like things that are soluble, there's probably one that's more soluble than the other. And that's a certain degree of solubility. And frankly, I'm just happy as going, soluble or insoluble. Now, these sets of terms deal with liquids. So we don't use the terms like solute and solvent, solution, all that sort of stuff. We say that, or soluble and insoluble. We talk about things that are miscible and immiscible. So liquids that mix together are miscible, and we went on later to find out that this was due to things being polar and nonpolar. And if they don't readily mix together, we say they are immiscible. So again, later on we learned that polar was a nonpolar molecule. Sorry, oil was a nonpolar molecule, and water was polar. And so they were not like, they did not mix. But that was in the next section. One of the other things we looked at was something called a solubility curve here. And we've got a whole bunch. So just a couple of features about our curve is it goes from 0 to 100 degrees Celsius, because that's the temperature that water is a liquid. These are always per 100 grams of solute. And just generally eyeballing it, you can see that for most of them, as your temperature increases, as temperature goes up, the amount of solid increases as well. Almost all of our lines are pointing up. We do have this one strange exception here. This one goes down, and that's just chemistry for you. There always seems to be some kind of exception, but generally, the warmer it is, the higher the solubility is going to be. We should also discuss too, perhaps, things. Why don't we take a look at KCl here? So KCl is this blue line that's right in the middle. And a lot of these questions ask us, what type of solution do we have? So it'll say at a certain temperature, you've got a certain amount dissolved. Is it saturated, unsaturated, or supersaturated? So with respect to KCl, if ever we have a point that is above the line, that is a supersaturated solution. If ever we're talking about a point below the line, that's an unsaturated solution. And if ever we're talking about a point on the line, that is a saturated solution. So we've got super, we've got saturated, and we have unsaturated. Now, these types of questions here, we can just kind of eyeball this. This is like specifically with examples, and then giving specific answers. So this is not about soluble or insoluble. So the first one is at 70 degrees, how much KNO3 can you dissolve? So you go up to 70 degrees, and then you're going to move up till you hit KNO3. And, well, that maybe is a bad example because this one's off. Okay, so that's not going to work. Let's change that to, I don't know. Let's change that to 40 degrees. Let's see. So 40 degrees will actually work better. So you're moving up, you hit the line, you go across, and then going across is going to tell you how much is soluble. So at that temperature there, it looks like you could probably have a ballpark about 65 grams. So that means you can At that temperature, you can put 65 grams of this KNO3 in the water, and it'll be a perfectly saturated solution. Another one here is NaCl at 100 degrees. So again, you move to a Hunji, you go up till you intersect, and then you just read across. Looks like it's about 40. I won't bother with those examples. So anyway, that's the whole point there. And that was section 1. Okay, into section 2. Section 2 was quite a long theory lesson, so I just sort of picked out some of the highlights here. So this whole section, we were talking about forces of attraction between molecules. Okay, so when we're talking about between, we're talking about intermolecular forces. And we were to go on that there were 3 types of intermolecular forces that are holding liquids together. And they are things that are polar, nonpolar, and really every liquid's going to be either one of these 2, right? You can classify any liquid as polar and nonpolar. Well, there's a third bonus force as well, the hydrogen bonding force. And this would only apply to some polar molecules. It's like a bonus extra force. So just a little bit about polar molecules. These are covalent compounds in the liquid state that have a dipole. So this harkens back to our electronegativity. Remember, those are numbers on the periodic table. So here's a molecule like HF. You look these numbers up. I think fluorine is 4.0, hydrogen's about 2.1. So that means in a bond, electrons are going to navigate towards the fluorine. So you're going to end up with a positive end next to the hydrogen and a negative end next to the fluorine, and that gives us our dipole. So I always think of this as there's a plus sign right there that's pointing the way to the dipole. And I guess that would be the end, and the arrow points to the negative end. So all polar molecules will thus have attractive forces for other polar molecules. Of course, when you have something that's positive and something that's negative, they're going to attract other positives and negatives. And this type of molecule lacks symmetry. You can always tell where that H is. If you made this molecule and held onto it, you could see that, yeah, no matter which way you turn it, you can tell that you've got a hydrogen and a fluorine, maybe even just based on the colors. Nonpolar molecules, these are covalent compounds that have no dipole. So something like this, again, it's very symmetrical. No matter which way you hold it in your hands, it always looks exactly the same. There's another one. So you can't really say this area is positive or this area is negative. And these ones do have lots of symmetry. Like I said, you can hold them and you can't really tell them apart. The third extra force here is our bonus force, and for our purposes, we're saying it's only occurring between hydrogens and oxygens. So a good example would be water. It's got hydrogens and oxygens. Oxygen is the negative part, and hydrogen is the positive part. So once you've got something that's positive and negative, you start to have some attractive forces for other water molecules. So there's some attractive forces, then you got more over here, and it just sort of keeps going on and on and on and on. So a good example of how these sort of work would be if you take a glass and you fill it up with water. You guys know that you can overfill it. You got that meniscus. You can put more water in the glass can hold. And that's because of these attractive forces between the hydrogens and the oxygen. It's just like they're hanging on to other hydrogen molecules and not letting them fall over the edge. So a quick little application of this is when we want to find, say, perhaps, organizing these from highest to lowest boiling point. Be careful about the type of question I ask. Sometimes I'll ask highest, sometimes I'll ask lowest. And it's really just based on their attractive forces. So we've got oxygen, we have water, and we have hydrogen sulfide here. So if you want to go ahead and classify these and you drew them out, that's what oxygen would look like, that's what water would look like, and that's what the hydrogen sulfide would look like. So in terms of classifying this, we could say that the oxygen is polar. Again, it's identical kind of in every direction. The water is, we've already identified it as polar, and we also identified water as having that extra hydrogen bonding force. And then our last one is polar as well. So we have 2 polar molecules, so those ones would sort of battle out for our highest boiling point. And really, it's going to be this one with our highest boiling point because it simply is polar and it has this extra force. This one's going to be second because it's just polar. And then this one will be third. It's our lowest one. And that's just because those oxygen molecules are kind of like neutral molecules. If you go ahead and actually looked up their boiling points, oxygen's minus 183, hydrogen sulfide is minus 60, and water's 100. So there you go. We just proved it by using our rationale and referring to the bonus forces. Good. Continuing with section 2, miscibility of liquids. So why do some liquids mix with others? Well, others don't. And we did kind of talk about this. So it's really coming down to organizing things as being either polar or nonpolar. Like dissolves like. So polar solutes will be miscible with polar solvents. Again, I use the word miscible just because they're both liquids. Nonpolar solutes will be miscible with nonpolar. So in both cases, we have like solutes and solvents in terms of intermolecular forces, polar and nonpolar. And then, of course, the other scenario is where one's polar and one's nonpolar. Well, they're not going to mix. They will be immiscible. So what happens when you mix water and milk? You probably already know this one. Yeah, they'll mix. We know that they will be miscible. Well, what do we know? Already know that water is a polar molecule, meaning we've just discovered that this milk must also be polar. Continuing on here, water and oil. You put those together, they do not mix. They are immiscible. And what we can conclude is that knowing water is polar, if they don't mix, then oil has to be nonpolar. And oil and grease. Well, you might not know that what happens here, but they actually do end up mixing. They are miscible. So if oil is nonpolar and they're going to mix together, that must mean grease is also nonpolar. I don't know what's going on with that funny marker there. So grease must be nonpolar. So that's how you can use kind of your brain to figure out if things are going to mix with each other. That was section 2. Section 3 was molarity, and it measures the concentration of a solution. So how strong, how weak, how diluted is that solution going to be? Don't forget molarity is big M, and it's measured in moles per liter. And C equals N over V we use quite extensively the rest of the section here. Don't forget, too, that you can rearrange the formula to perhaps solve for N, and that can then you can take that a step further and maybe solve a question with grams, like how many grams do you put in 500 mils to make a 0.2 molar solution, something like that. And even a third version would be the volume formula. So in our future mole map, we actually kind of have seen these two already. And that one's actually on the mole map as well. Section 4 was about dilutions, and that's just adding water to a solution. The whole point is to decrease the concentration. And there's a straight up C1V1 equals C2V2. Works exactly the same as Boyle's law, just it's about dilutions. So commonly, if you're doing a dilution, it's just you've got one substance and you're adding a bunch of water to it. Concentration will go down. Volume goes up, concentration goes down, number of moles stays the same. Okay, section 5 was where we got introduced to a couple of theories of acids and bases. The first one was our Arrhenius method, and we learned that acids produce H plus when they are in water. So an example here would be you just want to break HCl up into its two ions. Notice it's aqueous here, that means it's aqueous here and aqueous there. Now, bases produce OH when they are in water solution. So if you take a compound like this, you're going to break it up into the two ions, which are barium that has a charge of +2. Just check the periodic table for that. And we have two of these hydroxides. So because there was a 2 here, I had to put a 2 right there. And again, notice everything is aqueous. So Arrhenius method was good. It works a lot of the time, but not all the time. And that was the problem. Doesn't work all the time to classify everything, so there needed to be a second example, or second theory, I should say, which was our Bronsted-Lowry theory. Now, this one focused on acids giving up hydrogens and bases accepting hydrogens. So, a couple things, and I'll try to write an example here. Let's see what happens. Oh boy, I don't know why that's flashing up, but here I'm going to do this. Let's switch views. So let's take any old acid. Let's take H2SO4 aqueous, and we're just going to move one hydrogen. Now, a couple key features of the Bronsted-Lowry is that water is one of our reactants, H2O. straight arrow. The type of arrow was section 6. And now it's all about taking one hydrogen and moving it along. So we're going to take this one hydrogen right here, and we're going to bring it over to that side. So what do we have left? Well, we still have a hydrogen because there were 2, now we're down to 1. And we still have that SO4. And it's in the aqueous state. Now the molecule H2SO4 started neutral. We took away a positive. Well, it must have a negative charge now. Now the other product we formed was we started with H2O, and we put an extra hydrogen on it. That gives us H3O. And we learned that that H3O was the hydronium ion. That's like the acidic molecule, so that one's kind of a big deal. Now, another thing we did at this point was we labeled our acid-base conjugate pairs. Those are a pair of molecules different from one single H+. Even before I get that, we should probably label this. The very first thing here was sulfuric acid, so its name is acid, has to be an acid. Water accepted that hydrogen, so this must be acting as a base. Once you got that, then you can it's probably safe to go ahead and do your pairs. So these two here are going to pair up. So if this was an acid, that makes that a conjugate base. And these two are going to pair up. If that's a base, that makes that the conjugate acid. So that works quite well for all acids. And really there were sort of 3 scenarios here for figuring these out. And the first one is what happens if I literally give you an acid, which is what happened in this example. So you can call that A if you wish. B is a scenario where I tell you that, it's either acidic or basic. So let's pretend something is basic here. And let's do NH3. That will work nicely. Again, because it's the Bronsted-Lowry. This should be Bronsted-Lowry here. We're going to use the water. And this one actually has a double arrow. Don't worry about that. So we know, because I just said it, that this result is going to be a basic result. So all that means is that one of our products is OH. The only way we can get an OH is while taking a hydrogen away from that. And if you take a hydrogen away that's positive, it's going to have a negative charge. So we're taking one hydrogen from here, bringing it over to that molecule. That must make us result in NH4. And I'll put a little aqueous beside that. Then we make our, so we should label this, don't get too far ahead. So this water gave up the hydrogen, it's acting as the acid, this is acting as the base. Then we'll pair them up, acid goes with conjugate base, and then that must be acid there. So that's the second scenario where I give you the result. So it's basic, so that's why we wanted to make OH. If I'd said it was acidic, we would try to make H3O+. The third scenario is what happens when we start with a molecule that it has a charge to it. And we learned, like, this ammonia right here is not happy with itself. It doesn't want to have a charge. It wants to get back to neutral. So it is going to go ahead and give one of its hydrogens over here to the water. So it's back down to NH3, neutral. And we have created H3O+ here. So let's see, this one acted as the acid, this one acted as the base. These pair up, conjugate base, conjugate acid. Good. And again, not surprising, that's the conjugate acid because that's the acidic molecule. Not surprising, that's the conjugate base. It's the basic molecule. So there we go. There are your scenarios when it comes to this stuff. Okay. Back to my slideshow. Section 6 was just an attachment onto Section 5, and we learned a couple of things. We learned that acids completely ionized use this kind of arrow, and it means that there are only 2 things in solution, whatever made up the acid. Strong bases do the exact same. The words ionize and dissociate, they are essentially the same thing, and just bases dissociate. That means they break up. Acids ionize. Vowels and consonants going together. We also learned about weak acids that should say partially ionize, partially. And that means that we got a double arrow here, so that means you got products that make reactants, and then reactants that make products, and then products that make reactants, and back and forth. It's a big cycle, so you end up with everything in your solution And we also have weak bases, and this should say partially as well. So same thing. So the types of questions we came across here was, I would say, using the Bronsted-Lowry, show that this acid partially ionizes. So when I say partially ionizes, it tells you what kind of arrow you should use, and it gives you a bit of a direction on products and that sort of stuff. So that was section 6.
Dad, what school we do?
I don't know. Section 7. This was kind of a long one too. This was about the pH scale. I don't have access to it right now. Okay. It's downstairs in the basement. Okay, so the pH scale is what we talked about in section 7, and pH is all about, well, it's all about the acids, right? It's all about the H3O molecule. But all I wanted to say here was that our solution, any solution you have, has hydronium and hydroxide ions in it. So how's that possible? Well, anytime you have these two things, they're going to actually form water. So anytime you have water in this double arrow, you can see that water is breaking down to form these two things. And again, it's just a big loop. So we learned about our pH scale. We learned about acids being less than 7, bases are greater than 7. So there's our acidic range. Keep in mind, if you have 6.9, that is an acidic solution. 6.99, acidic. So I like to say anything less than 7. And so on our acidic area here, we get more hydronium ions than hydroxides. As soon as we cross to the basic area, we get more of the hydroxides, and of course, when they're equal to each other, we have a neutral solution. Now, we spent some time going over some equations here. So when we're talking about your pH scale, we're using the negative log. Remember that this has to do with a molarity or a concentration, okay? So if you know the concentration of a solution, you can take the negative log. All the negative does is turns your value positive, so you can put it onto the pH scale. So most of the time, you're going to use this formula. This is like the king of the formulas in this section. You can do the flip reverse, though. This is a little less common. This is where I'm giving you the pH and I'm asking for the concentration of the solution. It's a little less likely, but it's just something you can do on your calculator, and that's 10 to the negative pH. So you're probably using like x to the y for this one button on your calculator. We also learned that you can have sort of the opposites here. These were the exact same formulas, but frankly, you don't really need to worry about these as long as you're considering where your answer goes. So if you did an answer, if you figured out the pH of a base, you'd say, well, you know, pH of a base can't be 2. That doesn't make sense. You actually need to use this formula to go, okay, 14 minus 2 gives me 12. Well, 12, that's definitely an answer for a base. So yeah. Section 8 was all about sort of investigating a little bit further how things are existing in solution here. So in units 1 and 2, we looked at how things react. So we took NaCl and we said, okay, you know, it's going to break down into Na and Cl. You check the diatomic gases. You say, okay, that one's a gas, that one's a solid, you know, and you balance it. Now in unit 3, what we're talking about, though, is we're just strictly looking at NaCl and saying, okay, NaCl, when it's in the aqueous state, is actually made up of sodium and chlorine, and each of these has a charge to them. Well, that should actually be a negative charge, not a positive charge. There we go. So that's what we're investigating here, how these things break up. So we got a couple rules to worry about. Anything in the aqueous state is not existing as a compound. It's just breaking up into those ions that we just looked at. That's rule 1. And your other rule is anytime you have something in the solid, liquid, or gas state, that they're going to stay in those. They're not going to break up. That's our second rule. And that sort of governs us as we proceed. So here was a kind of a typical example. So we have to do a balanced chemical equation first. Then we're going to break up everything that's aqueous. Then we'll do some canceling out of stuff. And then whatever cancels is going to be our spectator ions. So I've got silver nitrate and aluminum chloride here. So this is where you grab your periodic table and you say, okay, silver and aluminum are going to switch partners. We're going to end up with AgCl. You check your rules and you figure out that that's a solid, and that's good. We can actually proceed with this. And the other product is aluminum nitrate. This one's not balanced. It's important to balance. So I'm probably thinking to myself, well, this has 3 nitrates. No, I guess I thought to myself, this has 3 chlorines, so I'll put a 3 in front of that. And then a 3 gives me 3 silvers on both sides, and that also gives me 3 nitrates. So that one's balanced. The next step is where I'm going to break everything up. So I'm going to start with that 3AgNO3 that's in the aqueous state that's starting it off, and I'm going to say, okay, well, silver nitrate is made up of silver and nitrate. Silver is positive, nitrate is minus. It's in the aqueous state, so I need to attach an aqueous. And because there's a 3 in front of it, that 3 goes with both compounds. Then you go on to the second one, that is the aluminum and the chlorine. You write their charges. You write there is aqueous, and then a little bit of balancing because we do have 3 chlorines in our formula, so we'll put a 3 in front. Arrow. When it comes to the 3 AgCls, it's in the solid state, so we don't break it up. That's the whole point of this question, is to see what ions are forming the precipitate. And then we've got aluminum nitrate, so we have aluminum and nitrate, plus 3 minus 1, aqueous, aqueous, and a little balance there. That would be your total ionic equation. As you get to your next equation, you just want to cancel out things that are the exact same on either side. So let's see, you just got to find things that are exactly the same. Like we have 3 aluminums, we have 3 aluminums. Or sorry, we have aluminum that's plus 3, aluminum that's plus 3. We also have 3 nitrates that are minus 1 and 3 nitrates that are minus 1. Once you've canceled, the net ionic equation is just rewriting the stuff that you didn't cancel out. There's that, and that's your net ionic equation. And then lastly, the things we did cancel out, those are going to be our spectator ions. Okay, section 9 and section 10, we now are maybe a little smarter than where we were at the time. These are mole map questions. We called it the mole plan at the time, but we now know better. We now know that we can use our mole map to solve these. So in section 9, we looked at questions that were liquid to solid and solid to liquid. So again, you guys grab your mole maps out and just follow those 3 steps along to solve those questions. And then in section 10, we realized that also mole map questions, these ones were liquid to liquid, which actually had a fancy name. These were titration questions. I don't think I wrote the word titration on here. Titration, and they involve an acid and a base neutralizing each other. When they neutralize, they end up sort of changing color because there's an indicator. And then at that point, what you can do is you can find the unknown concentration of one of them. Either it's the acid or the base. Now, sometimes kids get bogged down. They see a couple volumes and a concentration, and they automatically think that they're using the dilution formula, which is incorrect. These questions are not dilution, even though in essence we're given sort of 3 of the 4 things here. It's not a dilution because it's 2 substances reacting. It can't be a dilution. Dilution is just 1 substance and you're adding water. So yeah, with these ones, and mole map, grab your mole map and just follow the steps. The equations are literally on your mole map. Okay, so recording stuff.